So let's talk about today about trajectory optimization with convex optimization. Okay, so all right. So here's the motivation. So the trajectory optimization we've written down so far has been as a nonlinear program. Okay, so it's great. It can handle nonlinear dynamics, underactuated dynamics. It can handle nonlinear, even non-convex constraints, right? For instance, obstacle avoidance, we'll talk more about that today and see how that fits in. But the solvers aren't guaranteed to find a solution, right? You fail to find a solution even if one exists. So last time we tried to address that by telling you about one of the algorithms from randomized motion planning, the RRT. Which gave a form of completeness, a completeness in the sense that if I wait till time goes to infinity, I'll definitely find a solution. But in practice, these are effective effective planners for very complicated domains, and they are probabilistically complete. So I feel like I talked to a bunch of you afterwards, and maybe just by virtue of the order that I chose to present them, trajectory optimization first, and then RRT comes in looking like the solution. I think they both have their place, and they're good for different things. But actually, our group uses more trajectory optimization than RRTs. I don't want to give you the impression that the RRTs somehow fix all the problems with trajectory optimization. I think they're both different tools. They have different virtues, right? The RRTs give you random-looking paths and need some extra work afterwards. Typically, they take a lot longer to solve, but they solve a broader class of problems. Okay, but there are some trajectory optimization problems that are guaranteed to find a solution if one exists. Okay, and they can be made to solve a pretty broad class of problems with some extra work. So I want to talk today about that class of algorithms, right? Now, there's various versions of it that we could focus on. I'm going to choose, just so we don't bounce around too much, I'm going to talk about the ones that can be written down as just one particular type of convex optimization, which is a quadratic program. So I know you got to learn about linear programming on your last problem set if you didn't already know it. And we've mentioned quadratic programming a bunch. Let me just give the quick reminder or introduction, as it is, about what I mean when I say a quadratic program. Right, so a quadratic program is something that I can write down as a minimization of some quadratic function. And I can have linear terms in there too. I could have constant terms, but that would not affect my solution, so I'll leave them out. Subject to linear constraints. Now, almost always when we say quadratic program, we actually mean a convex quadratic program. The ones we can solve effectively are when Q is positive semi-definite. Then there's efficient algorithms to solve that, because it's the convex case. The non-convex case is NP-hard. So there are tools to solve it, but they're not in the realm of convex optimization. So the picture you should have in your head here is that you have some decision parameters, let's say Z1, Z2. These linear constraints give me some polytopic region. This is each one of these constraints is a linear constraint, a half-plane constraint. So it cuts off, says maybe I'm on this side of the plane. Another one says maybe I'm on this side, maybe I'm on this side. And you put them all together, since they all have to be satisfied, I get some region that's my convex region of feasible points. Satisfy those constraints. And I also have some quadratic objective, which is quadratic bowl. It sits on top of that. Even my colors aren't going to save me here, are they? But some quadratic bowl that sits on top of that. And I have to find within the set of feasible points the minimum of that quadratic bowl. And you can imagine that if it's upside down, then that's a lot harder. I could be smashing into any one of the corners, and that gets to be combinatorially bad. But if it's an upright bowl, then I go to the minimum. Everything's good. Okay? So it turns out that we can formulate some trajectory optimization problems as a quadratic program. And if we can do that, then these programs are guaranteed their convex optimization, just like we've been saying the whole time. If a solution exists, we're guaranteed to be able to find it and find it efficiently, right? So let's think about the cases where we can write an optimization, a trajectory sort of optimization as a quadratic program. Okay, so for instance, I can write down LQR as a quadratic program, or at least a finite horizon version of LQR. Okay, if I have a finite time LQR. All right, so let's do that. Let's do that on the next slide. So. We'll go ahead and discretize time just to keep it cleaner, but that's not actually required. It's required to discretize your inputs, but not your state. Everything's simpler like this. Okay, so I'll write down my linear discrete time dynamics. And let's try to minimize over some finite time my inputs. Somehow I'm getting extra clicks today. Of my quadratic cost. Okay, so maybe you can see already, but it's going to be pretty natural, actually, to write that down as a very large, potentially, quadratic program, but as a quadratic program. And we can actually do two different approaches to do it, right? You've already seen some different approaches to trajectory optimization. Either one could work here. In discrete time, collocation doesn't make as much sense, but we could certainly do either the direct transcription or the shooting approach. And you can write either of them down, and they're both a quadratic program here. So I could do the direct transcription. I'll choose my decision parameters. I was calling them Z on the other slide, but I'll do x0, I'm sorry, x1. x0 is given. To xn, and u0, un minus 1. Be my decision parameters. And then I can just write down some minimize over z, this quadratic function. It's going to be, call it h, some big matrix H, right? Where H is going to look like Q, Q, Q for a while, R for a while, depending on how I ordered them. Right? But if I line up x1, x2, u0, un minus 1, right? Same thing on the other side. Then I could write this cost function as a big, pretty empty matrix, okay? And then I can write these dynamics down as linear constraints on those variables, right? So they're equality constraints, but I can write that down as a pair of inequality constraints. Right? So I'll just write less than or equal to and greater than or equal to. That gives me my equality constraints. And A is going to be, this A is going to be a big matrix that has those elements in it. This B is going to be, right? Okay, so that works. And I can write down, given a linear dynamical system, my LQR problem as a very big, potentially, in the horizon time of the optimization, quadratic program. And in fact, I can solve it really fast. And QPs are pretty darn fast to solve these days. Okay, solve it really fast. So this one, certainly for any n goes to infinity, has a closed form solution. So I'm not sure. I have to somehow still convince you that there's something good about this, about doing this. The simplest way to convince you, I think, is that given this optimization, I can start doing all the things that I couldn't quite do before. Like I could put in my input limits directly, right? I could put in constraints. And I can still solve it. I can even put in state constraints if I want. Linear constraints, but if I have linear constraints, I can start dropping them on, and I can still solve it, right? The big thing I'm giving up, well, the first thing I'm giving up is I have to solve a big optimization, potentially big optimization problem. But again, that's cheap. Don't be afraid of that. The biggest thing I'm giving up is I'm solving it from a particular initial condition, a particular trajectory, whereas LQR so far we solved for the complete solution for the complete feedback controller. Okay, so one of the things that people do this, this is often called model predictive control. It's important, I'll put it in blue here. Sometimes this is, you can have a nonlinear version of model predictive control. Maybe this is often called linear model predictive control. And the reason it's called that is because I'm computing potentially with a big optimization a control from a particular initial condition. But a lot of times people will implement this online. The QP is fast enough to solve that you basically, I take my current state x, I plan for the next n minus 1 steps what my control action should be. I take the first one, I go one step, I see where I actually arrived at, recompute my solution for the next n minus 1 step, and just do it in a receding horizon way. And that's a way to turn a fast, guaranteed to succeed trajectory optimization algorithm into a feedback controller. Now you have to do that at your own peril for a general trajectory optimization, because you could be marching along happy with your feedback control, and then suddenly your trajectory optimizer says, sorry, you couldn't find a solution that time, and you're in some state that you didn't want to be in, and you're stuck, right? But if you have one that's guaranteed to succeed, then this is a great algorithm. Okay? Does that make sense? Yeah.
So why are you planning every time?
Because so this is a trajectory optimization. It's finding a particular set of u's, scalar u's, over time. It's not giving me a policy u as a function of x. So if there was no noise in the system and I moved one step, I'd be exactly where I thought I was going to be, and I could just keep using my original plan. But if there's noise in the system or a disturbance or something like this, I'm off my plan. I'll recompute given the new final horizon, the new horizon, and run again.
So you don't always be planning, only be planning your indefinite state that you didn't consider.
But in the real world, you're never where you thought you were going to be. So every DT, you replan. You could put just do it every time. Yeah. Because your model's wrong, and there's noise in your sensors, and there's all kinds of stuff. Okay, you could also do this with a, yeah, sure.
If the time horizon is the next time step, is it the same as deadbeat control?
When
you arrive at the next time step itself, like is it a subsection of this? Or?
Deadbeat control would be if you asked if my objective was to get to the goal in one step. So if I put in a constraint saying x at time 1 has to be my goal, then the thing that would pop out would be deadbeat control. But this is actually saying something slightly different, right? I can have a different. This is a quadratic objective the way I've written it. Yeah, but it's similar. Yeah.
So how do you impose long-term goals? So you want to reach some certain state in the future, and your horizon is not long enough.
Okay.
So you're just steering towards that.
So there's a couple things you can do, but a lot of times what people will do is if you don't have the computational resources to make n big enough, then what you can do is say xn, let's say, tack on some final cost, which would be, let's say, from LQR. So ignore your control limits, ignore the constraints that you can't handle in LQR, and just solve what would be the infinite horizon cost to go. And then I'll think about my constraints for n steps, and then from there on use the cost to go of the unconstrained problem. And that's actually what Scott was talking about. We're setting at n to 1 on Atlas. We're computing LQR for the infinite horizon, and then just instantaneously taking the cost, the input limits into account to go down to, yeah.
So assuming the system is linear, are the x's here in this case, are they actually like x bar? So assuming it's linear and we follow a trajectory, are the x's here at each case actually the error? Is this actually like, x desired minus where we want to be,
yeah,
or minus where we are?
So that absolutely works. It doesn't matter what your coordinate system is in the linear case. You could either change your coordinates to x bar here, or you could have your objective have a x minus x bar, or x minus x naught, and have some linear terms in your objective. Either one is still compatible. It could be written down as a QP. You get to pick.
Just one more question.
Sure.
Do people have guarantees that you will either go with respect to the noise in your the noise that you have in your system? Is that kind of guarantees that people have? Or?
So we haven't modeled noise here. In the LQG case, there are some guarantees if you put in Gaussian noise assumptions like that, and we'll talk about that soon. There are ways to use these in a robust model predictive control way, where you can sort of guarantee that you're going to go downhill in the cost to go from this. And actually, we're going to talk about both of those in the sort of noise and robustness lecture, for sure. But actually, for linear systems, linear plus plus, let's say, linear plus noise, linear plus bounded uncertainty, you are going to have very nice generalizations of this. Yeah?
How do you write your dynamics as AX? Do you use like finite differences?
So I shouldn't have said x there. Good catch. This is z. That's my decision variable z. Yeah.
Stack A.
And I really shouldn't call this a. Let's call it a bar or something like that, just to make it different. Good catch.
So if you're actually dealing with a nonlinear system, this is just a linearization. It works well and it's pretty small, like you're locally. But if you want to plan long term, you can only encode like linear dynamics here, right? And you wouldn't be able, you don't know where you're going to be, so it's not like linearized.
So you're getting ahead, but yes. So
Is that why you guys do like one step with Atlas? Because locally you do look like AX plus.
locally, Atlas is linear.
Yeah.
If you drop in Q, if you know your state,
Yeah.
then the dynamics are actually linear for one step.
Yeah, but like
And
in a
long
sense,
term, it's
then
not.
You'll be somewhere else.
That's right. So the question of how you use this, so you could use this for nonlinear trajectory optimization. One thing people do would be, they call it iterative LQR. You can actually do nonlinear trajectory optimization by picking having your initial trajectory, linearize it, use this. It's like a sequential quadratic programming update, but it's a slightly different update, where you basically use this to say what would the linear system have done if I optimized it,
Okay.
and then relinearize what would the linear system have done. And that is in spirit, very similar to the sequential quadratic programming updates, but it's numerically different. And some people believe it's an important difference. And that's typically called ILQR or iterative LQR, and that's an algorithm that people have in the trajectory optimization world. And a slight variation of it is called DDP, Differential Dynamic Programming. And it's almost the same thing, but it turns out, so here we did more than that actually. We took a linearization of the dynamics and a quadratic approximation of the cost locally. In DDP, you can have a second order approximation of your dynamics and still solve it as a QP.
Okay.
And
But when you're optimizing, you like committed to the trajectory that you linearize your dynamics around.
yes,
Keep up.
and then you use that as make a
And
one
you
step
adjust
like
your
that,
matrix and
wash, rinse, and repeat. Yeah. Cool. I want to make sure you see that you can also write the shooting method down just like this. It also works. So if I were to have chosen my z to be just u0 to un, right? For linear systems, I can just solve away all those extra terms. My xk is just a to the k x0, right? This is just the solution marching forward of a linear system, but it's still, well, it's linear in the initial conditions and it's linear in my decision variables. So I can just stick all this into my cost everywhere I had xk transpose qx. I don't know why it's doing that today, but I can, looks like something from Carrie or something, huh? Everywhere I had this, I can stick in this big mess and still have something that's quadratic in my objective, right? And then this, of course, is just adding more quadratic terms. So that's a quadratic program with significantly less decision variables, less constraints. In fact, if you had no other constraints, you could solve it away in with least squares. Arguably, I mean, so I think for quadratic programs are so robust that it's not a big difference either way. You know, for some of the other solvers we have, the numerical conditioning of your problems makes a big difference. For quadratic programs, the solvers are good enough that they'll scale gradients for you and just take care of that mess.
Will you reach the same solution with those new methods?
Yeah. All right, so let's make sure we're on the same page here. This is a question for you. If I have an airplane, I'm going to draw a silly airplane, sorry. It's got a tail, yeah. And let's say I'm willing to make a linear approximation of the dynamics of the airplane. And I've got a goal here. And I've got an obstacle here. So can I write that down? Let's even say it's a convex polygon. Can I write that down as a quadratic program, the trajectory optimization from my current initial condition to the goal? What do you think?
You want to avoid?
I've got sure.
You want to avoid the.
So I'm going to minimize my my actuator input, let's say, and get to the goal.
If you want it to be in that polygon, you could write it.
Right. Right. So exactly. So the polygon, you can write down a polygon, the interior of a polygon, right, as a set of linear constraints, right? But the exterior, this is saying that, I mean, each one of these lines, just make sure each one of these lines is a linear constraint. If I'm saying I'm on this side of this, and I'm on this side of this, right, the interior of that is a set of linear constraints. If I want to stay outside it, you can't write that down. You want to. That's an or, right? I want to say I'm on this side, or I'm on this side, or I'm on this side, and you can't write that down as a simple matrix linear constraint, right? Unless if you're willing to, for instance, let's say I were to say that this is region 1, let me call it, I don't know, S1. And this, let's say this over here is region 2 when I'm on this side. And if I were to be willing to say, for instance, that x0 through xk are inside S1, and then xk to xn are in S2, then you could write that down. But I've had to somehow pick k as the time that I'm going to be in this intersection. Okay, we'll get back to that in a little bit. But I want people to really have a visceral feeling for the fact that that is a avoiding an obstacle is a non-convex thing, and I will not have a convex optimization that gets me there magically, right? It gets me a sort of obstacle avoidance. Okay, so one of the really cool things is that you can do is you can you can start asking the question. So this is a richer class than LQR now, because LQR gave me infinite horizon or finite horizon if I solve a Riccati equation. We had different versions of LQR, but we never had one that could handle the input saturations or state constraints. This one works for only from a particular initial condition, but you can actually go back and ask the question is how does this solution to the quadratic program change as a function of initial conditions? And that could sort of give you some sense of what the feedback controller that you would be getting if you were to run MPC looks like. And in fact, there's people that have advocated that okay, MPC works great, but you say it's too slow for your embedded processor. So we'll actually, there's something called Explicit Mpc, which will try to solve that feedback controller by running MPC enough times and evaluating, understanding the solution basically, and come up with an exact expression, which is the feedback controller from MPC. And that's an idea called Explicit Mpc. Okay, and the way to think about it is there's another type of problem, another type of mathematical program, which is called a multi-parametric QP, basically a parameterized QP. Think of it as just, a QP parameterized, a parameterized QP. It's got to be parameterized in a specific way. So if I were to write a QP, the one we've written down here is a QP that's sort of parameterized by x0. And in general, the form is something that I've got some x0 plus the min over my z, z transpose hz. I'm just going to throw in a bunch of big matrix symbols here. Those letters are not to be taken seriously. They're just big matrices, yeah. I debated whether to write that down at all for you, but just to give you a sense of the class of problems that are sort of the multi-parametric quadratic program. It's got a quadratic program on the inside. It's parameterized in a quadratic way by some parameters, which I've written x0 to be consistent. Okay, there's a very important result from the world of MPQP. It's theorem 1 in a paper I'll cite in the notes. And that is that if I look at the solution of this QP over x0, then first of all, the feasible solution, the feasible set, is polyhedral. I'll interpret this for you in a second. The resulting value function it's got lots of nice properties. It's continuous, convex, and piecewise quadratic. And the optimizer, z star, which is a function of x0 now, is continuous and piecewise affine. I'm going to show you pictures that make this click, I hope. So the unconstrained LQR problem, we know had a value function that was a quadratic pole. The constrained LQR is also it's piecewise quadratic. It's still convex. In every segment, the cost to go is a quadratic function, but it's put together with pieces of quadratic functions. The controller for LQR unconstrained is a linear controller. Now it's a piecewise linear controller. Okay, it's beautiful that they can prove this, and actually they prove it in general for these QPs, is that QPs have these nice continuous solutions. We've parameterized them in this way. One of the downsides is that the number of pieces is kind of out of this world, right? So it's upper bounded, which is probably really conservative, but it's upper bounded by the number of possible active constraints. So 2 times the number of constraints. In general, for every possible set of constraints, which can either be active or inactive, I have a different piece in my system. And I'll show you, maybe I'll do it now, but I'll show you that can get big. And so this is in my view, it's a theoretical value and less of practical value, but some people do advocate using this to solve things that I could compile down to a microprocessor, which would be faster than solving a QP on the microprocessor. Okay, so